Welcome, everyone. Thanks for coming tonight. As he said, you're in the Thoughtworks office here in Melbourne, or Sydney. I just came from Melbourne, so I'm not quite here yet. I'm based in Thoughtworks in the U.S., in the Atlanta office, but if you know many people from Thoughtworks, we travel a lot. And I'm here tonight to talk about stories every developer should know. And the genesis for this talk came about because Mark Richards and I, who's a really well-known figure in the software architecture world, he and I do these software architecture fundamentals workshops at a variety of conferences. This is part of my 10,000 hours is doing these talks at conferences. And one of the things that we notice always is that one of the problems in the software development world is there's always so much new cool stuff coming at you that you never pay attention to the old cool stuff that is in the past. And there are a lot of really important lessons from some of that old stuff. And so as we're teaching these classes for software architecture fundamentals, I would say, well, you know about pets.com, of course, because that's why we now have elastic scale. And everybody goes, no, we don't know about pets.com, or, you know, or the IBM San Francisco project, which was the grand experiment. And can we reuse things to a ridiculous degree? But nobody knows about that either. And so that's why I decided to put together this talk about stories developers should know. And this is, a lot of times stories work better than hard cold facts because you've been listening to stories your whole life. I mean, your parents read you bedtime stories. You're used to the structure of stories and the way they put together. And sometimes, you can give somebody a dry list of facts and not sway them, but tell them an evocative story and make a better case for it. So I'm going to give you some evocative stories and maybe make some cases around DevOps or architecture or reuse or some of the other things that I touch on along the way. One of the things I got really fascinated with really early on, I actually started out of the traditional engineering world and then moved into software engineering. I got really fascinated for a period of time on this field of engineering called forensic engineering, which is basically the engineers that go, when things break spectacularly, these are the engineers that go up and figure out why. And this is a really cool job. And there's some really cool books about this. And then I realized at some point that there are only like a few hundred people in the world who do this. And so it's a really hard job to get. And so I kind of lost that fascination. But a lot of what I'm going to talk about today turns out is sort of forensic engineering, both of the physical world and of the software world. So let's talk about some stories that every developer should know. And the first one I'm going to talk about is the oldest one by far. This is the story of the Vasa. And this goes all the way back to the 1600s. It turns out that the king of Sweden, King Gustavus Adolphus, was at war with the king of Poland. And they'd been in war for a long time. They were both kind of tired of this war. And so they had decided, the king of Sweden had decided, I'm going to create the ultimate weapon and end this war once and for all. And so he had the best shipbuilder in the world at that time working for him. And they'd grown a special forest outside the castle of the special wood. And he felled the forest to make, whoops, pointer. That was not meant for a dramatic effect. And ended up designing this magnificent ship, the Vasa. And so at the time, ships typically were either gunships or they were troop transports. The Vasa was going to be both. Most ships at that time had one deck. This was going to have two decks. Most of them had one row of guns. This had two rows of guns. So everything, it basically doubled everything that the Vasa would do. These are actually pictures of the Vasa. I'll show you where you can go look at it now if you're curious. And like I say, this was going to be the ultimate war weapon because normally what happened was you had boats that shot at people or you had boats that had troops on them. This was going to roll up to the shore of Poland, shoot at them, and then roll a bunch of troops out on them. That was going to be, a big surprise. And so they designed this thing. This is what a cross-section of the Vasa looked like. The people who were designing it were kind of trepidatious about whether this was going to work or not, but they had to follow the orders of the king, so they kept building this thing. And so they had twice as big of guns as had ever been on a ship before. Everything was twice as much as anything had ever been before. So they finally finished this thing, and they set it out, and they shot off a salute off one side of the ship to celebrate the ship going out to sea, and it promptly capsized and then sank to the bottom of the bay there in Sweden. It turns out the water there is extremely cold and extremely anaerobic, almost no oxygen in it. So the Vasa was preserved until the early 1900s, until it was brought back up. And so this is one of the two architect/developer field trips you should make once in your life. One of them is to Sweden to actually go see the Vasa, because it's there in a museum. You can go see the real Vasa in all of its glory after they pulled it up out of the water. There's a model of it, but there's the actual ship is there, and you can see it as this great folly to trying to build the most magnificent ship ever. But what happened there as they were trying to build this ship? Well, they'd built a bunch of cannon ships before, and they'd built a bunch of troop transport, 2-deck ships before, but they'd never built one of these that did both at the same time. And this is a common problem that we encounter in the software world, where we have something that does a job, and we decide it needs to do a different job completely. And we think we can take and preserve the things that it already does and make it do a whole bunch more stuff. It turns out that almost never works in software. And many of you discover this the hard way as you take a monolithic kind of a thing and try to convert it into some kind of services or microservices kind of thing. You'll discover that all the architectural characteristics are now completely different, and all the trade-offs are different, and everything is different about it. But this really talks about the nature of the job of software architecture, because when you think about software architecture as a craft or profession, and you're trying to solve some problem by building software, you have requirements of some kind, regardless of how you got those. But that's not the only thing you have to think about as an architect. There are all these other things that come into the equation. Things like performance and scalability and auditability and all these extra characteristics that you have to think about. And in fact, really the craft of architecture is putting together the requirements and all these other things and crafting some solution that actually trades all these things off in a useful way and makes some sort of cohesive, defined architecture. And this can get messy sometimes. And some more about this in just a bit, about how far you should go in that direction. But here's the problem we always have. And you see this pervasively in systems we build, in frameworks that we build. Everything always starts nice and simple and elegant and solves a real problem. And every time something solves a problem, people say, well, it should also solve this problem. And it should also solve this problem. And this problem. And before long, you have an enterprise service bus. But this happens every time. There's a great blog entry by Bruce Tate, a really great writer, who talks about in the very early days of Java, he got this pet monkey called Java. And he was playing with it, it was fun, he could do all this cool stuff. And then one night, Java stayed up late at night and ate a book about XML. And the next day he was kind of surly and, kind of now, talking about schemas and stuff and a bunch of other, And, now Java stayed up late one night and learned about distributed computing. And now he's wanting to build those. And he finally said, I had to get rid of Java and I got a cute new dog called Ruby. And of course now, Ruby becomes, and every time you take something that does something useful, you keep making it do more useful things until it becomes the thing you were trying to get rid of, and you burn all that down and start over from scratch. We keep doing that over and over. One of the things that we need to learn better as architects is when somebody says you should take this ship and build one that's never been built before, have the confidence to say, no, maybe we shouldn't do that. Of course, it's hard to do that for a king because they will execute you. It's a little better for project managers. But this is really fundamentally a misunderstanding of how all these trade-offs really play off one another, which is something that plagues us a lot as well. So my second story is about the Tacoma Narrows Bridge in Washington State in the U.S. This is a bridge that spanned the Tacoma Narrows Strait at Puget Sound between Tacoma. This is in the northwest of the U.S. And this is a bridge that was open to traffic on July 1st, 1940, and then closed to traffic on November 7th of that same year for reasons that you will discover quite soon. So this was exemplar of a bridge design that was quite common at this time. This is a more modern, nicer version of one of these bridges, but it's a suspension bridge which has a metal platform and then has suspension cables to hold the thing up. And what had been happening was they'd been designing these bridges for a while, and they kept pushing the envelope on them to make them a little bit lighter, a little bit thinner plates, a little bit narrower cables, and see if we can keep pushing the envelope. And here's what happens when you push that envelope a little bit too far. So this is why the bridge eventually closed in 1940 on September 1st. Why is it not playing my video? Here we go. Here's my video. So the problem was when the wind blew at a very certain pace in this river gorge, the bridge would start buckling and wildly and bounce up and down and all this other crazy stuff. People nearby thought it was cool and would go and ride it like a ride while it was bucking up and down. There are videos of this where people are walking on it and they can't walk because it's pitching back and forth, until one day in 1940 it finally collapsed into the river gorge because the tolerances were just too great. They did not accounted for the wind and the particular frequency of wind that happened in that river gorge. The name of this bridge became known as the Galloping Gertie because it would bounce like that so much. But this is another example of trying to scale architecture too much. We got something that worked, and so let's keep pushing the envelope on that until you eventually get to the point where it breaks. And so this is an example of designing right up to the edge, taking a proven concept and pushing it till it breaks. But what's interesting about this bridge was at the same time, in the same era, there was another bridge designer working in Sweden, coincidentally, called Robert Majort. And this is one of his bridges. I can't pronounce that because it's in Swedish, but he built these bridges using this radical new material called reinforced concrete with arches on them. And he built bridges that the math of the day said would not be stable and wouldn't stand up. But he was very experimental, and so he didn't believe all this math. Of course, math has now justified and vindicated what he was talking about. But he built a lot of bridges like this using this design. And this is, in fact, one of the most common bridge designs you see now today, reinforced concrete with stiffened arches like this. He also designed these column heads, these mushroom-shaped column heads that turns out that distribute weight much better than traditional column heads and crack much less than traditional column heads. And he also designed these sort of through trial and error and trying some things. And he had 3 design principles that he utilized when he designed stuff like this. Value calculations based on simple analysis, carefully consider the construction process to make sure you don't mess it up as you construct it, and then test the structure always with full-scale load tests to make sure that it works correctly. So when he'd design a bridge, he'd roll heavier and heavier things across it to see exactly what his tolerances were. And so rather than take a theoretical design like the suspension bridge and then push the envelope on that, what he did instead was took a very experimental approach to bridge design, which is push the envelope a little bit, then verify through experiment that it worked, and then rinse and repeat. Push the envelope a little bit more and verify did it work, and that's where you find the tolerances where things break on models, and you can find, without getting into that scaling problem, you can ease up to that edge a little more gracefully. My next story is the F-16 fighter jet, which came about in 1974. And what's interesting about the F-16 was the Air Force went to Northrop Grumman and asked them for a Mach 2.5 aircraft. It turns out in 1974 that was a very difficult thing to achieve, because if the materials were light enough to get to Mach 2.5, it would vibrate apart as it accelerated, and they tried lots and lots of things and they could not come up with a solution to this problem. And so they eventually went back to the Air Force and said, okay, we're having a really hard time meeting this requirement. Why do you need it to go Mach 2.5? And they said, well, these things are expensive, so if they get in a dogfight, we want them to be able to escape really quickly if they need to. Now that Northrop Grumman understood the actual requirements, they went back and built a Mach 2 aircraft, the F-16, but it could accelerate really, really fast, and it was the most maneuverable aircraft that they ever created up until that point of time. And this gets back to one of the things that we constantly have to do in the software world. This gets back to the thing I defined before, that really software is a combination of requirements plus all these external factors that you have to take into account. Some of them are explicit, some of them are implicit just because of the nature of the problem domain that you work in. We call these things the illities of software architecture, but there's one really critical illity that I don't think architects and developers use enough, and that's feasibility. Should we even be trying to build this thing? And this is more pertinent to architects now than it was 10 years ago, because we have a different perspective on software systems than we did 10 years ago. Because 10 years ago, as an architect, you had no awareness whatsoever in what happened in operations. That was a completely different silo. Most of the time it was outsourced to a completely different company. You could send them tickets and eventually get stuff to happen, but there was no interaction between those two roles. But now, in modern architectures, operations is really part of architecture, and now you have a much better perspective over, is it even feasible to do the thing that we're trying to do? And sometimes you should say no, or think about a different way to do this. But this gets back to this annoying question that we have to do as architects all the time, as the annoying 3-year-old thing of, well, why do you need that? But why do you need that? But why do you need that? Oh, that's what you need. Okay, then now we can actually build a system that is both feasible and does the stuff you want to do, because very often users give you solutions rather than problems. And it's very often your job to get to the actual problem away from the solution, because you'll end up building some crazy thing that you don't actually need. There's a famous case where this group of engineers got this requirement, and it required a 0.1 second response time. And like, ooh, boy, that's a meaty problem. And they did this really elaborate design that would enable that, and they showed it to the business, and the business was like, wow, this seems crazily over-engineered. Why all this? And it's like, well, we're trying to meet that 0.1 second response time. And they said, oh, no, that's a typo. It should say 1 second response time. But they never asked that because, hey, it was going to be cool to build this, really responsive system, and that's not actually what they needed. So next, I want to talk about Null, everyone's favorite subject. Somebody had to invent this thing. It wasn't a part of the universe before we came along, and this is the guy who invented it, Sir Tony Hoare. He takes responsibility for this in a talk that he refers to as Null references the billion-dollar mistake, and he asks that you please do not bill him for this. But he is the one who created the first language that had Null in it and has pervaded in all the languages since then. So let's talk a little bit about where Null came from, because most of you don't even think that was invented. You thought it was just part of the universe as the universe was formed, but somebody had to invent the idea of Null. So if you look at the history of computer programming languages, this is a chart you can download from O'Reilly, which has a brief history of computer languages. And we're familiar with the ones certainly that start in the middle here, this whole Java family. There's Oak, which is the progenitor of Java, which became Java 1 and all the family of Java code. But I'm interested more in the ones that came before Oak and the ones that led to Oak, like this red guy here, and this there's ANSI C up there. It was one of the progenitors. And there's Objective-C, so let's back up a little bit in time and see some of these progenitors that led up to that. So there's C, one of these guys is Pascal, there's a COBOL up there, there's a Smalltalk. But if you keep going back a little bit further, what you'll eventually find is this guy, Algol 60, which was created in 1960. And the language that Tony Hoare created was based on Algol 60. It was actually one of these Algol 68s, I believe, was the one that he created, which is incredibly influential to a bunch of these languages that came a lot later. So he worked for a company, Elliott Computer, at the time, that made computer hardware, and they also made a compiler for Algol. And here's some Algol code. It looks very Pascal-like. This is actually influenced Pascal on a whole bunch of the languages that came after it in the structured programming revolution. So that's what Algol looked like. And Tony Hoare talks about when he designed the language. Now we're talking about here very early days of computers, and so very, very limited resources. And so one of the things that was really common up until that time was kind of a Wild West attitude about things like array subscripts, and not a lot of safety in array subscripts. And he thought very diligently about, should I build these protections into Algol? And actually built a version of the language that had a protection for array subscripts, had an initialization language so that you couldn't initialize something, basically protected against null pointers in a way that you would recognize in a language like Java now. And he actually built a version of the compiler with a switch in it that you could turn this feature on and off for good type safety and checking and all that. But then This is a commercial computer company. This is way before open source. So Elliott was selling hardware and they're selling alcohol. So they ask a bunch of their customers, hey, do you want this really safe language with all the safety stuff in it? And they resoundingly said no. Which seems odd. Because wouldn't you want something that's a lot safer and a lot better than the one you had before? Here's the problem. The problem is, when you create a new language like Algol, you've got to convince people to write in Algol. And there are not a lot of Algol programs out there, and you've got to sell computers before there's a groundswell of Algol programs out there. So one of the first things you do when you create a new computer like this is create a translator from the old languages into the new one, and the pervasive old language at the time was Fortran. And it turns out that a really common technique in Fortran was to cheat horribly on things like array subscripts. There are all these techniques in the Fortran language of cheating on array subscripts and wrapping around and a bunch of other stuff. And it turns out that any reasonable Fortran program would instantly break if you try to put type safety and any kind of checks around it. And it slowed Algol down enough that it made it not a good competitor in the market space. And so he decided to build Algol without any of these checks in it, and therefore open the door to having this idea of null in it. Because if you look at this history chart, here's the Algols. Look at this thing that comes down here. What is that? That goes all the way back the very first programming language, which is Fortran. Legacy is why we can't have nice things. We'd love to have a language now without null in it, but we can't because we have to be backwards compatible to the thing that has to be backwards compatible, that has to be backwards compatible to the first stupid thing we ever created when we didn't know anything about computer languages. But we still have to be backwards compatible to everything that has ever been, which is why we can't ever build any beautiful, nice, elegant thing, because we're always carrying all this baggage with us everywhere. And this is a pervasive problem in software, is reuse. How do we effectively reuse stuff without abusing it to death? And this subject will come up over and over again. And this is actually the trade-off that he faced when he was thinking about this, is safety versus speed. And we see this kind of trade-off all the time in software, and he definitely went the speed route in that case, and of course we still have nulls because of that. But these kind of decisions, these seemingly simple decisions, have these long-standing kind of implications. And there's a great example of this in Java, the modern language. So Brian Getz is the chief architect of Java now. And if you ever meet Brian and you want to see one of the veins start sticking out in his forehead and see him really get irate, start talking to him about serialization. Which is baked into Java at the deepest level, because when Java was created in the mid-90s, distributed computing was all the rage. And the people who created Java said, well, it's obvious that all programming in the future is going to rely heavily on distributed computing and three-tier systems, and so we're going to build the ability to serialize any object in Java and put it on the wire and build it at the very core of the language. And now fast forward to 2017, and Brian Getz is trying to figure out how to serialize a lambda. Makes no sense whatsoever, and yet he has to be able to do that because they cooked it in at the bottommost level of language. So every single design decision they make in Java has to be filtered through the stupid, well, what do we do about the serialization thing that has to be considered, because it is essentially an attack vector way to initialize things without constructors. That's essentially what serialization is, and so there's all these things that you have to think about. And the long-term implications of things, simple decisions like that, it's really, really hard to trace, how far those implications are going to go. So the next thing I want to talk about is Ada. And this is a picture of Lady Ada. She's interesting historically because we can point to her as the very first programmer in history. It's kind of unusual to be able to point to a single individual and say they're the first person to ever do this activity, but we can pretty safely do that for Lady Ada. She lived in the mid-1800s in England, and she was actually Lord Byron's daughter, and she knew Charles Babbage, who was toying around with steam-powered computers, and actually designed 2 steam-powered computers, the difference engine and the analytical engine. It turns out the precision steam parts are going to be too expensive to build, and so they never built one of the things. She was a mathematician that was hanging around, and she actually wrote some programs for Babbage's difference engine that she never got to run because they never actually built the computer. They built one of them a few years ago and ran one of Lady Ada's programs through it, and it had a couple of minor bugs in it, but it would have worked fine. So you can point to her as the very first programmer in history. That's not really what this is about, though. This is about something that was named after her. And so the Department of Defense in the US in 1975 realized that they had a big problem, in that they figured at that time they had rewritten the degrees to radians conversion routine in more than 2,000 different programming languages, and it wasn't getting any better. They would constantly have to rewrite the same code over and over because every little division of the military wanted to use their own programming language. The bigger problem was some of these were embedded systems and the manufacturers going out of business, and now you can't get support and other stuff. And so they realized this is a problem, and so they put together the high order language working group to try to identify, is there a language we can use across all military stuff for real time versus all these other systems. And so they tried to figure out if that was true, and they got together, and by the mid-80s they realized it was not. And so they decided to create a new language and named it Ada, named after Lady Ada. This fell into the brief period of time. So in the early 70s, we had structured programming languages. At the late 70s into the 80s, we had modular programming languages, and then the object-oriented languages came along in the early 80s. So there was this brief time where we had modular programming languages, and that's where Ada fit in. It was modular. It was meant to be really readable. So here's some actual Ada code. Every keyword in the language was an English word except else if. So it was very readable. Had this header header and implementation, kind of like C. And so they implemented Ada and started mandating that every DoD project use it, and it worked. They were using more than 450 languages in 1983, and by 1996 they were down to 37 languages, most of which had gone to Ada. And Ada is still used for a lot of things. The avionics on the Boeing 777 is written in Ada. So a lot of airline, because it's really good real time, and there's a lot of safety protocols built into it. But then in 1996, they started moving away from Ada, and they're no longer standardized on Ada, so it's a bit of a backwater right now in some specialized places because they realized a couple of things. In the mid-90s and going into the 2000s, they started buying a lot more commercial off-the-shelf software, this kind of COTS software, rather than building their own, because they realized there was a headache when you build your own stuff, because when you build it, that means you own it forever. And I keep running into companies who have done this. I did some consulting with this financial services company in New York, in the US. And they had built their own application server. They'd built their own terrible version of struts. They'd built their own Corba protocol. And at one point I said, did you build your own operating system? And they said, no. And I said, why not? You built everything else from scratch. But here's the problem. They built their version of struts before struts came out. So they were on the bleeding edge of this kind of model view controller, web framework kind of thing. And then struts came out. And they had a decision to make. Should we take our craptaculous homegrown, 80% of struts thing and move it over to actual struts, but there's going to be a little bit of pain there, or should we keep our thing? And they doubled down on their thing. Over and over and over again. The problem with that is, now, a decade later, the very best developers in this country are on full-time maintenance mode for their own craptaculous struts, their craptaculous application server, their craptaculous Corba orb. The amount of brain power they're using to half-ass implement the things that you can download for free is just amazing. And they're not doing any kind of innovation because their best developers are struggling as fast as they can to keep up with what the rest of the world has already outpaced them with a million times over. And that's exactly what these guys realized, is that, you know, it's way easier to rely on the rest of the world to build this stuff and validate it than it is to build it and own it and maintain it yourself. And what you end up with is a lot of sort of forced over-engineering when you try to impose too much standardization on things. Because that's what happened with Ada, is that it ended up being used for a lot of wildly unsuitable things because it is not, it turns out, not one programming language that solves every problem on Earth, no matter how much you'd like for it to be. And so they discovered a lot of the hazards of over-standardizing. And I'll come back to this because this has an interesting sort of intersection with reuse here in a second. But next, I'll talk about the Ariane 5. This is very much in the forensic engineering realm. This is a commercial rocket that delivered satellite payloads to space. These are unmanned rockets, so the crash I'm about to show you, the only thing that was lost was some satellites and some things like that. But this has happened in the early 2000s. This is the launch of the Ariane 5. We'll see it 39 seconds into launch here at an altitude of 2.5 miles. You'll see it swerve wildly off to one side. That swerve caused the auto self-destruct mechanism to kick in on the rocket and caused it to self-destruct itself. So what I want to talk about is what caused the swerve to happen right there at 39 seconds into the flight. So once they did the forensic engineering on this thing to figure out what happened, here's what they learned. It turns out that the Ariane 5, guess what it was based on? The Ariane 4. Seems logical. And the Ariane 4 was also a rocket that had a bunch of stuff in it. The Ariane 5, of course, is a much better version. It turns out that the Ariane 5 had a 64-bit flight data recorder. And the Ariane 4 had a 16-bit guidance system. But when it came time to implement a guidance system for the Ariane 5, they said, bah, we don't need to write a new guidance system. We already got one of those. We got one of the Ariane 4. We just take that and use it in the 5. Problem solved. More code we don't have to write. So cool. So what happened was, 39 seconds into the flight data recorder tried to take 64 bits worth of information and cram it into 16 bits worth of flight data guidance system, which didn't work. Turns out some of those bits might have been important. And that's what caused it to swerve off to the side, because the guidance system got some nonsensical data from the flight data recorder, said this doesn't make any sense. That caused the course correction, and that's caused the thing to actually blow up. But here's what's really frustrating about this. So that guidance system, that 60-minute guidance system that they reused from the Ariane 4, part of the problem is version 5 was faster than version 4, and they tried to reuse it. But here's the really frustrating thing. That guidance system from the Ariane 4 was only used while the rocket was on the ground. This is the thing that lets you know where you were on the ground. That's the part they had reused. But it turns out that it takes a long time to reboot that guidance system. And it was crashing a lot in the early days of the Ariane 5, so they thought, you know, rather than have to wait for this thing to reboot every time, let's just keep it running for the first 40 seconds of flight. You know, so we don't have to restart it. And 39 seconds is exactly when that happened. And of course, what these guys are doing is debugging in production. And of course, this caused their rocket ship to blow up when they did that, because that first 40 seconds, of course, 39-second mark is exactly when that mismatch happened between those two things. But this is a problem of debugging in production. This is a problem of legacy code. This is a problem of something that I refer to as abstraction distraction. And this is a really nasty problem for us, because we all fall into this problem all the time. So here is the problem. If you look at something like the technology stack from 2005 or so, you could change the labels on those boxes, but there's not that much difference. I mean, there was kind of, you know, multi-tier, baby multi-tier kind of stuff. If you look at a similar technology stack from 2016, lots more moving parts. The problem is every single one of those moving parts is built on an abstraction, not a real thing. It looks like a real thing, but it's not quite. They all leak just a little bit. They're never perfect. Abstractions are kind of summaries of things, and you see this in Java with the file system. It's an abstraction of a real machine, but we got to have a real file system, so there's some weird leakiness that goes on there. This is what I refer to as an abstraction distraction. The problem is, the more complicated your stack gets like this, you get all these abstractions resting on these other abstractions as if they were rock solid, and they're not. And eventually what happens is you get some really low-level bug or error that bubbles all the way up and yields you a 3,000-line stack trace. And this is like wandering into your pond into a backyard and the Loch Ness Monster pops up. And it's like, what are you? And where did you come from? And how am I going to chase you and kill you now? Because who knows what 3,000 lines of all these things ended up happening. The problem is we lean on these abstractions and we forget that they're abstractions until they suddenly go away. So what is your first thought when you see this screen? How much have I lost? Because suddenly all of your abstractions have now gone away. All of your files and folders and all the nice organization you had has now plummeted into nothingness. And now you're trying to think, ooh, when was the last time I saved all that stuff? That is the essence of this idea of abstraction, distraction. And that's exactly what they suffered from too. Because somebody knew that the Ariane 4 was 16-bit, but you get so used to this idea of int. So, it's just an int. Well, you pass ints around, and you forget that these are fundamentally different size things, and they live in different worlds. So my next story is one I mentioned before, pets.com. There's probably not a fighting chance of you guys remembering pets.com. You may actually remember this thing. Does anybody remember this sock puppet mascot? Yeah, a couple of you from the U.S.? Yeah, that's why. So pets.com in the very early internet era came out, and they were going to be the Amazon of pet supplies. All the things you need for your pet could be purchased at pets.com. And they created this mascot and a huge marketing campaign. This thing was like at the Super Bowl, making commentaries. I mean, everywhere. You couldn't get anywhere without the sock puppet thing showing up everywhere. Turns out what they did as a company was they spent a lot of money on their marketing. Not so much on like infrastructure. Turns out their marketing worked. And everybody went to pets.com to buy stuff. So much so that the site would fall over and they'd lose transactions. It got so bad that they just completely ruined their reputation. They were eventually acquired by PetSmart in the early 2000s only for the sock puppet. That was the only thing of value the whole company had, was the stupid sock puppet. So the marketing department killed it, but everybody else, not so much. This is the classic example of too little infrastructure, but this is terrified architects. Because this is one of the first cases where a company was so successful that it destroyed them. And before the internet, physics made that impossible. Because you couldn't make a space big enough to get enough people in it to destroy your business. But the internet, all the bets are off. And so architects took years after this trying to figure out elasticity. This is why we have elastic scale right now. It's because of pets.com, because we figured out, what if we have this worst problem and we're so successful that everybody and their brother wants to come and buy something from us? We've got to build elastic scale, and this is really what inspired that idea of what we now know as elastic scale in cloud. And we built a lot of very complicated architectures, like space-based architectures to manage this stuff, to make it happen. Because this is the fundamental problem we were attacking. This is the problem that Amazon attacked before they changed their architecture. What happens if you're super successful and you have this architecture? This was exactly Amazon's architecture in the early days. Well, as soon as you get hammered here, you add more web servers. What happens now? Your app server gets hammered. So you add more app servers. Then what happens? Your database server gets hammered. Now what happens? Oops. This is exactly where Amazon hit and realized we can't, there's no way we can scale this. They literally could not pour enough hardware and effort into to scale this. And so this is the architecture I mentioned before, space-based architecture. It was created not too long after pets.com, which actually had all this elastic scale built into the architecture. It was crazy, complicated. You could actually purchase these things. These were tuple spaces, like Gigaspaces did this. Several of these things have actually converted into giant distributed caches now. So Confluent started as one of these things and then converted into a giant distributed cache. And of course, this was really the inspiration for the kind of elastic scale we have now in microservices. And this idea of being able to do elastic scale at the service level has become very popular. And that's really the end of the story from the pets.com era. But you know, in the pets.com era, it was really hard. Because if I wanted to create a booming business, I had to have a pile of venture capital cash this high to buy servers and network infrastructure and databases and all that other stuff. Now with cloud resources, you can lean on that, even if it's more expensive initially to prove a case, and then convert over to your own infrastructure. That's exactly what Dropbox did. They started out on Amazon's cloud and then moved into their own private cloud once they proved their business model. And so now you have commodity elastic scale, which is an amazing thing to have if you go back to the pets.com era, which nothing like that existed. So pets.com is one side of a spectrum. Webvan is the other side of that spectrum. This is a service that was kicked off in the US around the same time as pets.com, and they were going to deliver groceries to your house. Now, they actually have some services in the US now, the gig economy, that do this, but this is way before that. This is before people had smartphones and that kind of stuff. So this is one of the Webvan vans. I actually took advantage of this service because I was one of the few cities they were in. It was awesome. But they were really trying to be like the premier quality store at bargain prices that would also deliver to your house, which is a really hard thing to achieve. But ultimately what they failed was they did the opposite of pets.com. They went crazy with infrastructure. This is one of their warehouses for groceries in one of their cities. They had they would sell cigars, and they had these enormous humidors, bigger than any specialty cigar store, within these giant warehouses. That was one of the reasons they failed, because they built this enormous amount of infrastructure. But here's the other reason they failed. So here's the US. The first Webvan rolled out in California. The second one was Washington. The third was Chicago. Now, if you have a business that's heavily reliant on physically moving perishable things around, wouldn't you think you'd build them a little closer to one another? Because the next one was there in Atlanta, which is the one I got to take advantage of. And then the next one was up here in Cincinnati. So they're trying to build all these hubs, all these crazy expensive things, and they just failed utterly because they spent all their money building all this really cool stuff, and they had way too much infrastructure to support any kind of sales they had. But this is the problem you see in software of let's build all the frameworks we need first, and then we'll be easy to build the thing that we want to build. But that never is the case. You end up spending all your time building your frameworks and never the things that you need. But this is another case of misunderstanding what the real trade-offs of that business are fundamentally about infrastructure versus size and scale, et cetera. So my next two are the two scariest ones. This is the scariest one for sure, Knight Capital. If you ever want to find a good reference to this story, all you need to do is Google the phrase bankrupt in 45 minutes, and you'll find a good reference to the Knight Capital story. So here's Knight Capital. This is a really cascading series of terrible engineering decisions. So this is a commodities trading company based in New York, and there's the SEC in the US has special guidelines for algorithmic trading, and there are all these guidelines they have to meet. And a new one had just come out called SMARS, that Knight Capital is going to have to implement this algorithm for SMARS by a certain date. And so, okay, we're going to have to implement SMARS. And so the first tragic mistake they made, because the old way that they've been doing trading was this thing called PowerPeg. Turns out PowerPeg was still in their code base underneath a feature toggle that was turned off. And some genius at Knight Capital said, hey, we need to implement the SMARS code. Why don't we just implement that underneath the old PowerPeg feature toggle? Because, you know, coming up with a new name is so hard. Like, you know, SMARS. I mean, who would ever, come up with a new name like that? Because that's the name of the thing that they're trying to build. So, okay, we'll be lazy and implement the new smartest code underneath the old PowerPeg feature toggles. So that's strike one. Never reuse old feature toggles. I mean, come on. But you'll see what happens. And so they implemented the new smartest code. And they put it live on 7 of their 8 servers. Because they didn't automate this. So I'm sure their operations guy, he's installing the new smartest code. He gets number 7, and then something shiny happens. And he gets distracted, and okay, well, yeah, we're all done with that. And so now it's time to go live. And so they go live on August 1st, 2012 is when this happened. And they flip the PowerPeg switch on. 7 servers start doing SMARS. 1 server starts doing PowerPeg. Turns out SMARS is selling, PowerPeg is buying. And SMARS is selling high, and PowerPeg is buying low, or whatever the bad version of that is. And so they saw this start happening, and they're like, this is not supposed to be happening. Why is this happening? It's got to be the new SMARS code. There's something wrong with the new SMARS code, so take the SMARS code off of all the servers. But they left the PowerPeg toggle on, which means now all 8 machines are doing PowerPeg. At about 45 minutes in, they realized what was going on and pulled the server's plugs out of the wall to make them stop, and had to get a check for $400 million by a venture capital firm that day, because that's how much in debt they were. That was the only thing that allowed them to survive the day, because they were so much in debt by this little fiasco that they had to get that much cash infusion to survive and figure all this stuff out. So what happened here? Well, okay, so lots of bad things happen. First, never reuse a feature toggle. That's just asking for trouble, because creating new names for things, so hard. Why would you ever go to that trouble of creating a new name for something? So that's a bad idea. The next is automate this kind of stuff. I mean, come on, do you even DevOps? This is the lesson that we learn from automating stuff, is you want consistency across things like machine images that do things. There's no value to having each one of those 8 things being slightly different from one another. But boy, there's all kinds of possibilities for fiascos, which is exactly what happened here. And this is a great case of reuse gone bad. They're trying to reuse something that never should have been left in the code base to begin with, and then they end up reusing it, and then terrible things happened. So this is definitely one that every architect should know about, is the IBM San Francisco project. How many people here know about the IBM San Francisco project? Okay, see, this is just tragic, because there's such good lessons in this. So in the late 1990s, IBM looked around at all these business applications and said, you know what? To us, all these stinking business applications look exactly the same. So we're going to build one last business application. It's going to be called the San Francisco project. And it's going to do everything a business needs to do. So we're going to have these modules for general ledger. We're going to have these modules for HR and inventory and all the things that any business might need to do. Here's some blueprints for how some of this stuff is going to fit together. There's the general ledger, accounts payable, accounts receivable, because they looked at, hey, every company does this stuff, so why don't we just build this one giant configurable thing? And the idea was, you as a company, you instantiate the San Francisco general ledger thing. I just tweak and 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 tweak until eventually you've modeled your business exactly. And we're done. We never have to write any more software. That was the idea of the San Francisco project. And they actually released 2 modules of this thing before they realized this was the stupidest idea anybody had ever had in software. Because here's the problem that you run into with this, is that you've now got to model every single business process for every single company on earth in this configurable thing and test every combination of all those things to make sure they all work together and maintain all those things forever in all those different various places. But there was this idea that was really prevalent at the time, and they were chasing this idea, and it's this idea that I refer to as canonicality, single sources of truth for things. This was the thing that pervaded things like SOA kind of architecture. Because as an SOA architect, you were looking for opportunities to consolidate things. And I'll talk more about that in just a second as I talk about reuse and this philosophy and how it went wrong. So in August 1997, they released the San Francisco Foundation Utilities and the Common Business Objects. They started trying to actually implement stuff in this and realized that that was not going to go well. And so they decided at some point that the foundation and utilities was all just trash. They could throw that away. But you know, IBM hates to not reuse stuff. It's just so ingrained that, you know, we built all this code. This is the largest Java project on earth for a while. And they've realized now that, you know, it's kind of a dumb idea. But we got to figure out how to reuse some of that stuff. And so the Common Business Object became something you may have heard of called Enterprise Java Beans. So that's where all the work from the San Francisco project ended up in the session in Entity Beans in EJB. And so that was the most generic part of that that came out of the San Francisco project. The other thing that came out of this were several books about the component framework, which has a one review on Amazon that's 5 stars, which I can only suspect is the author's mother. I mean, could this have been like the most popular book possible for one person out there that's like, this is my book, I finally found it. There's another, this is the design patterns. This actually has a foreword by Martin Fowler, so this is how popular this stuff was back in the day, because he was a well-known figure at the time as well. And it's kind of interesting to go back. I actually own a copy of this book, which I found at a used bookstore. And it's fascinating to look at what they were pitching, because a lot of the architecture they were talking about was heavily using reflection, a bunch of other things that are kind of sketchy if you're trying to build, you know, a 100-year piece of software. So there was kind of interesting design decisions there that probably would not have worked out well, even if the fundamental idea hadn't been flawed. But fundamentally what it suffered from, and what a lot of other software suffers from, is something that we talk about in our Building Evolutionary Architectures book, which we refer to as the last 10% rule. So here's how this works. So many, many years ago, I worked for a consulting company that did software projects for clients in Microsoft Access. And we eventually shut that part of the business down because every Access project started as a booming success and ended in total failure. And we wanted to understand why that dynamic seemed to happen over and over again to these projects, and we codified this as the last 10% rule, or the last 10% trap. So here it is. So if you look at something like Access, what the user wants, about 80% of that is super fast and easy, and it's stunning how fast you can get there. And people are always shocked. It's like, wow, it's amazing how much you've gotten done in a short amount of time. The next 10% of what you want is possible, but difficult. Because now you're trying to do something a tool doesn't really want you to do, but you can kind of bend it or hack it. And well, it doesn't really want to do that, but you know, if I redirect this query into a view and then generate a report off of that, then I can filter that and get it to do the thing I want to do, kind of thing. But then the last 10%, you can't get underneath the tool or the framework enough, and you cannot get that last 10%. And it turns out that users always want 100% of what they want, and they're never satisfied with less. This is the last 10% trap. And this is, so some of you had a gray hair to remember the 4 GLs. Remember the 4 GLs? The 4th generation languages, Power Builder, FoxPro, DBase. Where'd they all go? That was all the rage in the late 1990s. That's what everybody was using, was 4 GLs. Where'd they all go? Why do we not have them anymore? They all suffer from the last 10% trap. You can get almost to the point where you could build a real thing, but it's like, just not quite. The other thing that suffers from this is every ERP tool on earth. Because you think about it, they demo great. Because SAP or PeopleSoft come in, it's like, look, we can model your business exactly. Just tweak, you know, and some BAP, you know, and some tweaking. And so the first bit I was going, oh, it's great. Look, our business, you know, our business is taking form. And then there comes a day. It's like, oh, well, yeah, the tool won't do that. So you can either bend your business process toward the way the tool wants, or we just won't model that part of your business in the tool. And then that starts happening over and over again. Those ERP projects never end up successful. They just agree to stop working. because they're about 4 times over their original projection in time and date, and they're nowhere near finished, and they're never going to get finished because of this last 10% trap. It's exactly what the San Francisco project suffered from. Anytime somebody's trying to sell you the most ultra generic piece of software, it's always going to suffer from this because you can't get underneath all of that stuff to configure it enough to get real stuff done, which is why we're still in 3rd generation general purpose programming languages to solve problems, because they let you get to a low enough level to solve those things. By the way, the 4GLs, they became DSLs. Ruby on Rails is a 4th generation language that's written embedded inside a 3rd generation language. And so is Gradle. And so what the 4GLs became are domain-specific languages written on top of really powerful 3rd generation languages. But this, again, is toward that idea of reuse again, and how can we do reuse better. Now, IBM went crazy with it and had to pull way back. So the next one I want to talk about is the Chandler project. And this is for all of you who are constantly whining about projects that have too many time constraints, or we have a budget, and all these things that we have to worry about. The Chandler project is about a project that had infinite time, had infinite resources, no legacy to have to deal with, and still failed utterly. There's a book called Dreaming in Code that is about the Chandler project, and it's worth reading. But if you are a professional developer, there are trigger warnings in this book, for sure, because as you're reading this book, about halfway through the book, you'll start saying, no, not another meeting. Oh no, they're doing another meeting. No, not another meeting. Please, not another meeting. Haven't we done this enough? Because that's what really became of the Chandler project, was meetings. So Mitch Kapoor, the guy who created Lotus 1-2-3, so for all the other people with gray hair in the audience, do you remember Lotus Agenda? So one of the other things that Lotus created was this piece of software called Lotus Agenda. It was the first intelligent PIM. So this ran on DOS, and it was the first tool where you could say stuff like, lunch with Jack next Tuesday. An agenda would figure out, oh, Jack must be this Jack in your address book, and I know what the date is, so next Tuesday must be this, and lunch is at noon, so I'll put an appointment in your address book with this contact at noon next Tuesday. It was magic in the DOS world, and so that was Agenda. When Mitch Kapoor sold Lotus 1-2-3, he wanted to create the new modern version of Agenda, a really super powerful piece of software that he was going to call Chandler. And that's what the origin of Chandler was, named after Raymond Chandler, the detective novelist. And it was going to be this personal information manager that would do all this really cool stuff. And so he was very ambitious. He wanted to be a desktop application, but he also wanted seamless synchronization over the internet, which was a really hard thing to achieve at that time. He also wanted this ultimate malleability. So an email would become a calendar entry or a task, or you could shift and morph all these things from one thing into another. And so he gathered this team of rock star developers together. He's a billionaire, no money constraints. Hired the best developers he could find anywhere and told them, we have no budget constraints, we have no time constraints, we're trying to create an ultimate piece of software. And so they started having meetings about designing stuff. And they designed a data store. And they decided they didn't like that data store. So they had some more meetings about things. They designed another data store. So they decided they didn't like that data store. So they had some more meetings about stuff. And then they had some more meetings about stuff. And at one point, the author left. Because the author of the book, Dreaming in Code, had come along to document this fascinating open source project with none of these constraints. And then he's waiting around. So a year passes, 2 years pass, 3 years pass. They're doing a lot of meetings. There's one guy, Andy Yates, who's from the original Macintosh team, who's running around trying to get them to write code. Every time they create a new database, he actually produces some code that uses that database. Like, look, it's no, let's have a meeting about that. And so the author of this book finally just said, you know what, I got to get on with my life. These knuckleheads are never going to get anything done. And so he finished the book without them finishing the project, because he figured they're never going to finish this project. And he was pretty much right. They eventually did limp to the finish line with this, which you can sort of download. It is basically a very weak calendar that has some limited task management stuff in it, and that's it. None of the magic stuff, none of the distribution stuff. And this was, I'm guessing, about 15 years after they started the Chandler project, and at least $100 million, or probably way more of Mr. Kapoor's money by that time. And they basically limped to the finish line and released version 1.0 and then shut it down. This is like, we got to release something to show that for all this work that we did, we've got to release something. And so they released this and said, okay, that's it, we're out of here. But here's the problem they fell into, and this is a problem I see in a lot of large corporations, particularly really big ones. And it's this problem that meta work is more interesting than work. So if you really boil it down to its essence, if most of you are trying to describe your job to your grandparents, it is take things off web pages and put them in databases, and take things out of databases and put them on web pages. Yeah, there's a bunch of details in there about some other stuff, but at the end of the day, that's kind of what happens. And when you've done that for 10 or 15 times, it's kind of boring. You know what developers do when their day job is boring? They invent cool puzzles to solve. So they'll have cool puzzles to solve when they come into work. And I have to worry about all that boring stuff. That's what people use branching for in version control. It's not managing versions, because there are way better ways to do that with feature toggles. That's to create an impenetrable puzzle that you can beat your head against every day when you come into work. Git's awesome for that, because Git's really complicated. Boy, you can sit and think for a long time about a complicated problem with Git. That has nothing to do with taking things off a web page and putting them in a database, and vice versa. I was talking to a group of developers. So this is another suspension bridge, San Francisco Golden Gate Bridge. And it turns out that there's a crew that paints the Golden Gate Bridge. And the water in San Francisco is very caustic, and so it takes them about a year to paint the whole thing. And when that year's over, it's time to repaint it again. So they have a full-time job. They just paint the Golden Gate Bridge. So I was talking to a bunch of developers in one of our clients not too long ago, and I was talking to the head of architecture, and he said, yeah, we're currently in the process of ripping out all the Angular stuff and replacing it with React. And I said, is there a big business driver for that? And he said, no. Just seemed like a good thing to do. And I realized he's just painting the Golden Gate Bridge. Because he's realized, every time we go talk to the business people, they keep asking us stuff and, wanting stuff from us. But, if we're doing this, we're busy. Hey, we're busy. We're painting. We're busy. And, once that's done, at the end of the year, there'll be another web framework out. And we can just go to that one. And so we're always busy doing something. That's meta work is more interesting than work. And a lot of projects fall into that because, it's kind of boring. And so you invent puzzles to solve, which is generally not a good thing. So my last one, and I'll summarize some of the stuff, is your other field trip that you should take as a developer or architect. Also in Europe. This one's in Spain, in Barcelona. The weather's much nicer in Barcelona. This is Sagrada Familia. This is a basilica created by a famous architect here in Spain, Gaudi. And it's this incredible inside. It's meant to look like a forest inside. So it looks like a Dr. Seuss structure outside. They're still working on it. They're supposed to finish it in 2026, I think, which is one of the anniversaries of his death, or some famous anniversary for that. But this is the pillars from the inside that are meant to look like trees. So all of these pillars branch up and create these arches and these flowers, these crystal flowers embedded in the ceiling, all this amazing stuff. So there's some of those pillars that you see. These are all pictures I took there. And all the colors, so one side is all red stained glass and the other side is all blue stained glass. And so, the juxtaposition of those two things together is really amazing because you walk in, one side's one color and one side's the other. Here's an idea of the scale of the thing. So here are actual people and how tall the thing is from the inside. So it's a really magnificent work of architectural art, but that's not the reason you want to go see it as a developer and architect. You want to go see it, but then you want to go to the museum in the basement underneath, because that's where it explains how he designed Sagrada Familia. Because it turns out that when he started on the design for this, he didn't have nearly enough math. Nobody really had enough math to figure out all the weight bearing of all those arches that he was trying to create in those ceilings. But he also understood this principle that the way things deform by gravity is the same as weight-bearing structures deform, as when weight deforms them. And so what he did was built a model of what the church was going to look like with strings and sandbags. And the way that the sandbags deform the strings is the way the arches form to be weight-bearing when you actually build the structure. So this is a model of part of the cathedral done upside down sandbags. Here's a picture of it from the side. So you can sort of see the structure of how those columns come together inside it. When you look at this, if you look up here at the top on the ceiling, you'll see people to scale. And so when you flip this around, that is the cathedral. It's fascinating because this is a great example of something that I showed in the first story, which is this kind of experimental way of attacking problems that have not been attacked experimentally before. We see this in software all the time. When Amazon built their architecture, nobody had ever built an architecture like that before. They experimented with it and found a way to build this innovative architecture. Netflix is another great example. All of their chaos engineering stuff. O'Reilly just released a book on chaos engineering. That's a huge topic right now, and they've pioneered that. And they have a great take on that because it's not a question of if your system's going to fall over and die at some point. It's when. And why are you pretending that you can live in a world where it's never going to happen when you can live in a world where you can mitigate the certainty that that's going to happen? But that's another great example of this experimental architecture that nobody had ever quite done before. There's a great example of an architecture called LMAX. It's another one of those. They were trying to maximize the total fastest number of transactions a second. They managed to achieve 6 million transactions a second on a single Java thread, which is a really impressive architecture. So LMAX is a really interesting thing to look at. And it's open source now. You can play with it. So there are all my stories. So what kind of lessons can we learn from all these things? There's, of course, the famous lessons from Santayana that those who don't learn from history are doomed to repeat it. And we see that all the time in the software world. But let's see some common threads that fall through all of these things. And one of them is misunderstanding trade-offs and getting trade-offs correct. Because you can see this showing up in a lot of these stories. Misunderstanding trade-offs, getting them wrong, misinterpreting them, etc. Another one that's pervasive in a lot of these projects is that meta work is more interesting than work. You see this in Chandler, you see it in the San Francisco project, you see it in a bunch of these places. Ada also suffered from that too. But the thing that ties almost all of these things together is our attempt in one way or another to reuse something. So for the Vasa, they were trying to reuse designs from ships before that didn't work well. Same for Tacoma Narrows, they were trying to reuse a design and trying to scale it too far. For Null, trying to reuse old code and trying to be backwards compatible to the very first thing that was ever written anywhere. For Ada, it was trying to reuse everything, trying to build single sources of every single thing. The Ariane 5 is trying to reuse old unsuitable code again. Pets.com, not nearly enough reuse. Webvan invested in reuse way too early, so they both missed on opposite sides of the spectrum. Knight Capital trying to reuse things like old toggles, which is a terrible idea. San Francisco project trying to reuse, well, everything, trying to build the ultimate reusable thing. The Chandler project trying to reuse frameworks and design and platforms and code and building everything to be reusable first before it's usable. Sagrada Familia reused design and some design elements that they had done before, he'd used before. But what about reusing code? There's a great observation by John D. Cook who says that we've been sold this idea that reusing software is like using Legos, but his observation is that software use is way more like organ transplant than it is like snapping Lego blocks together. It's way messier and awful than it is just, cleanly snapping two things together. And this goes back to something I alluded to before, one of those design philosophies in the kind of service-oriented architecture world, because you were meant as an architect in that world to try to identify this phenomenon. You can download these slides if you want pictures of them. You're trying to identify this phenomenon. So let's say that you're a big enterprise, you have auto and homeowners, you have commercial insurance and casualty and life insurance and disability and travel, and they all have the concept of a customer. Now back in this day, you were supposed to notice this and go, oh, hey, They all say customer. They must be the same thing. So we should create a single customer class and couple all these guys to them. And what we'll do is take all the business people and lock them in a windowless conference room and deny them food and water until they tell us exactly what that customer thing is, once and for all. But that never works because they don't know. And, you know, after you let them out of the room and they eat and drink something, you'll merge with another company tomorrow and it'll change fundamentally exactly what this idea of customer is. And that's what they were trying to do in the ESB world, is try to reuse as much of this stuff as possible. But they didn't realize, they thought that reuse was the purely virtuous thing. They didn't realize that the coupling they were introducing by reusing may be more harmful than the reuse's benefit. And that's exactly the opposite thing that we picked up in the microservices world. Because the problem is, when you try to build something to be reusable first, this is the San Francisco project problem, it's hard to reuse it for a single thing. This is one of the observations we made in the Evolutionary Architecture book. The more reusable code is, the less usable it is. Because if you build this customer thing that needs to work in 6 or 7 different contexts, if I need to instantiate it for just one of those contexts, I have to give it a whole bunch of information that I don't really care about, but it's required to instantiate one of these things. And that makes it that much harder to actually reuse the thing. And that's what we did in the microservices world, was say, you know what, duplication is better than that coupling. We'd rather fight the battle of duplication, having individual representations of those things, and then reconcile them through messaging or something like that, than we would having all that coupling going on. But see, here's how we learn small things along the way. Because there was actually a benefit in that ESB picture from one thing. Let me go back to that picture for a second and talk about the one place where that was actually beneficial. So what we were trying to do in this world is build all these super reusable little Lego kind of things. And we've discovered this is a disaster for business services. But the one place this is great was for these guys. Monitoring, logging, authentication, authorization, all those things that we really benefit from having a single version of those, and a single resource, those kind of operational coupling things. It's really nice to be able to unify those things together. But it really is not great to try to unify all those domain things together because they change, and that's kind of the essence of what we're trying to build. So let's talk about how we solve that problem in the microservices world, because a really common characteristic in microservices is this idea that each service is instantiated on top of something like a service template. And a service template is where you put all those common operational things that you actually want to couple together, like monitoring and logging, maybe authentication and authorization. And in fact, what you're seeing now in the microservices world is an extension of that idea with this idea of what's called a service mesh. And so now, instead of a service template, they're actually calling this thing a sidecar. So this is the observation. In the microservices world, each of these services is going to need some operational stuff, like circuit breakers, service discovery, maybe monitoring, logging, etc. And so why not start treating those things consistently and creating what they call a sidecar or service template for those things. And now we can have the same one of those in each one of our services. And the idea of a service mesh is basically just a dashboard wired to all the sidecars. And so now I can control monitoring and logging and those kind of operational concerns because they're all coupled together, but I haven't coupled all my domain pieces together. So we've learned a little bit more about reuse here, because in microservices, we are coupling the things together that benefit from reuse, and we're avoiding coupling things together that are actually harmed by that level of coupling. And so this is an example of we gradually learn things as we go through each of these kind of architectural places. So this is not to say you shouldn't reuse, but you should reuse code carefully and understand what the implications are, both good and bad. But let's talk about another side of reuse. And the 11 lines of code that broke the internet. It was a little over a year ago now, where this guy decided to take his toys and go home because he got mad about something, some slight in the JavaScript community. And for about 2 days, he took leftpad.io away. And for about 2 days, nothing in the JavaScript ecosystem worked, because this is a core dependency on Node and Angular and a bunch of other code. This made headlines about how much these 11 lines of code broke the internet. You know, no matter how many bad things you say about Maven, it never made headlines about how bad it was. So, you know, I'm just saying. But this is really a problem that is pervasive for us, which is the problem of transitive dependency management. And what's interesting about this problem, from my standpoint, it is uniquely ubiquitous across all of our technology stacks. So here is a not uncommon transitive dependency graph for a JavaScript project. One of the things I think people have misunderstood here is that when you take on a transitive dependency like that, you're getting benefit, but you're also taking on a burden. And I don't know if 11 lines of code is worth the trade-off of the management and the other stuff that goes with that, but clearly the JavaScript community have decided, yes, it is. There is an NPM that all it does is return true. And somebody created a version of that that returns false. So it literally says, I only return true, but they needed a version that returned false. So they created a version that says it returns true, but it actually returns false. So that's what's going on in the JavaScript world right now. One of my colleagues in the UK, who's no relation to me, we have the same common last name, makes a really interesting observation here that dependency management is going to be our go-to considered harmful moment. This is the famous case where Dijkstra observed to people there that maybe writing code with unstructured go-tos was not the best way to write code, and almost got kicked out with pitchforks and torches by the audience who couldn't imagine that. The first thing you have to do is identify a problem before you can fix it. So he's identified it, now you need to go fix it. But this is really, I mean, every language and platform suffers from this, and it's a real headache to deal with, and it's a little bit dangerous on some projects. So there's fortunately some tooling that's coming around to help this. This is a tool called Dependabot. What Dependabot lets you do is set up a level of indirection between you and the outside world. You pull into Dependabot and then pull from Dependabot into your projects. This allows you a level of governance to the outside world, so you're not wiring yourself to the crazy outside world, because there was also an NPM that came out about a year ago as a proof of concept, and they took it down after about an hour because they proved their concept. You know, NPMs can run a shell script as they complete their installation. And so this particular NPM, as it was finishing up installation, would run a shell script that did rm-fr/. So what it would do is remove all the other stuff from your hard drive and make more space for more NPM modules that you can download. Because you know, you need more space for more NPM, so we could free up all that space by getting rid of that operating system and all that other pesky stuff that you're not using. Mark my words, and you can only have to mark it, it's already happened. NPM is going to be a virus attack vector for developer machines. The Google Developer Toolbar has already been used as an attack vector against developers. We've got to be a little more diligent about how crazy we are wiring ourselves to things in the outside world. And so this is, again, goes toward this idea of reuse stuff, but try to reuse it very carefully. Reuse is a benefit, but it also comes with a little bit of a burden. And you can see this because we keep trying it and we keep missing it by little bits, and we get a little better at it over time, but we're still not great at it. And this is actually my favorite quote about history. The past is never dead. It's not even past. You're still dealing with it all the time. The next time you have to serialize a Java object, you'll remember this quote. So that's all I have. Thanks very much for coming, and I hope you enjoyed it.